All right, in this lesson we're going to look at logarithmic functions, or logarithms for short. And logarithms are really just defined as the inverse of an exponential function. All right, everything has an inverse, and we've dealt with inverses a little bit here. But the inverse of an exponential function is basically this thing we call a logarithm. And so when we kind of approach this, we're going to think of it in terms of exponential functions. And just like we learned to graph things like square roots by looking at a quadratic and then graphing the inverse, we're going to graph these the same way. Okay, we're going to think about exponential functions and then take the inverse of that to come up with what these things kind of look like and find out a little bit about how they act. So when we write logarithms, they're in this format. It's y equals log base b of x. And that's how we read this. Y equals log base b of x. All right, so log base b of x. That's how we read it. Where b has to be greater than 0, but it can't be 1. And that should seem familiar because that's the same restrictions right here. These are the same restrictions we had with exponential functions. The b value had to be positive and it couldn't be 1. All right, it had to be greater than 0 and it couldn't be 1. So when we think about the base here, keep in mind that the base that we see here is the same as the base that we have in an exponential function, y equals a times b to the x. These b values are technically the same thing, all right? Really, when we look at these, they're interchangeable. And we'll see when we go from logarithms to exponential form, the base remains the same. So when we talk about base of an exponential function and base of a logarithm, we're essentially talking about the same thing. We're referring to the same base, all right? So, for example, if I look at something like this guy, again, I want to graph this thing. So if I think about, let me think about the exponential function that goes right alongside this. The exponential function that I'm essentially graphing the inverse of is y equals 3 to the x. All right? And so when you think about y equals 3 to the x, you know that the a value here is 1 and the b value is 3, so we can graph it that way. Or let's think of this in terms of the ordered pairs here. If you think about the ordered pairs, if I've got -2, -1, 0, 1, and 2, if I were to plug those in, that gives me a 1/9, a 1/3, let's see, a 1, a 3, and a 9. Think about the inverse of that as being the ordered pairs when we switch the x and the y. So my first ordered pair, let me think about the inverse. If I switch that, the inverse that's going to be a 1/9 -2 is going to be down here. And then 1/3 -1 is going to be right here. And then instead of 0, 1, I'm going to have 1, 0. Instead of 1, 3, I'm going to have 3, 1. Instead of 2, 9, I'm going to have 9, 2, which is out here somewhere. And so what I end up with is I end up with this curve, kind of hugs the hugs the y-axis, and then increases from there. So I get this curve that looks like this. And now, again, remember, think about inverses. Remember, inverses are reflected over this line. Think about what the graph of the exponential function would look like. The exponential function is going to look like this as I go to plot this thing. All right, it's going to hug this line and go through these points and shoot up forever, and that's terrible. Looks like, try that again. Oh, that's much better. Okay, but we can see it's reflected over that dotted line. So a logarithmic function kind of looks like an exponential function, but turned on its side. And really, the really interesting thing here that I want to point out is like here the b value is 3, so the exponential function increases, and that's why it's exponential growth. Well, here the b value is 3, and look at the logarithm. It increases as I go from left to right. It's increasing the whole time. It's going up as I go from left to right. So it's still increasing. So it still follows that same rule that if the b value is greater than 1, we're going to increase. If the b value is between 0 and 1, we're going to decrease. Okay. So again, the thing that I'm really interested in is the graph in blue. I only graphed the exponential function so we can see that it's the reflection of that. So when you graph these things, think about them as the inverse of an exponential function. Think about the ordered pairs that we've had with that exponential function, and then flip each of them. Likewise, if we look at this one, again, the exponential function that I would think about here would be y equals 1/2 to the x. And if we think about the ordered pairs that go along with that, let's see, that's going to be a 4, a 2, a 1, a 1/2, and a 1/4. And so if we think about flipping each of those ordered pairs, let's see what the graph of the inverse is going to look like. Instead of -2, 4, I'm going to do 4, -2. Instead of -1, 2, I'm going to do 2, -1. Instead of 0, 1, it's 1, 0. Instead of 1 1/2, it's 1/2 1. Instead of 2 1/4, it's 1/4 2. And so we can kind of get a general idea what this thing's going to look like. It looks like it's going to hug this line and go down this way. And notice, once again, this one is decreasing forever. And if you think about the inverse compared to the graph, it's going to reflect over this line. Think about what the graph of y equals 1/2 raised to the x is going to look like. It's going to look like this. Okay, it's going to hug this line and go up this way. Okay, and so these are reflections over that line. So again, we're just graphing the inverse of an exponential function. And so what that looks like is a sideways version of this exponential function. So think about the ordered pairs we would have for the exponential function, and then flip each of them, okay? And again, the b value being between 0 and 1, it's decreasing the whole time. As I go from left to right, we're headed down, we're decreasing, okay? The main thing we're going to look at with these is converting back and forth between exponential and logarithmic form, all right? If I have a function that says y equals log base b of x, I can rewrite it as x equals b to the y. I can take that logarithm and rewrite it as an exponential function. Likewise, if I have an exponential function, I can go back the other way. Notice this arrow goes both ways. If I have x equals b to the y, I can rewrite that as y equals log base b of x. So I can convert back and forth between exponential and logarithmic form. The important things to note here, always start with the b value. Notice the b value, the base is the base in both scenarios. Here it's the base of the logarithm, here's the base of the exponential function. And then the other thing is, because these are inverses, they kind of undo one another, they solve for one another. Notice that the logarithm is solved for the exponent over here. Normally in the exponential function, the x is in the exponent, the unknown is in the exponent. So the logarithm is solved for the exponent. The exponential function is solved for what's inside the logarithm, okay? So if you remember that these are inverse, they solve one another, they undo one another. The exponential function is solved for the logarithm is solved for the exponential function. That only leaves one value left to place, okay? So when I look at this, again, we're just memorizing these forms, memorizing where these things go. They're easy to memorize if we understand the nature of these things, all right? So if I look at the first one, I want to convert these to logarithmic form. So again, I'm going to start with the base. I know it's going to be log base 2. See, the base of the exponential function is 2, so the base of my logarithm is 2. And now from here, remember, logarithms are solved for the exponent, so it equals the exponent. That's the r. The only thing left to go inside the logarithm is the 7. So it's r equals log base 2 of 7. And you see the advantage of writing this as a logarithm is that there's no other way I could solve this for r. The only other way I know how to solve an exponential function so far is to get common bases. Well, here I can't get common bases. But I will learn eventually to plug this logarithm into my calculator, and then I can get a decimal approximation for what this exponent has to be, okay? Next one, same thing. I start with the base. It's going to be log base 5, because that's the base of my exponential function. It's going to equal the exponent. The only thing left to go inside is the y, all right? So it's 2 equals log base 5 of y. Next one, again, I'm going to start with the base. So it's log base 2. It's going to be equal to the exponent, that's the n. The only thing left to go inside here is the 32. So n equals log base 2 of 32. Next one, again, I'm going to start with the base, log base x this time, because that was the base of the exponential function. It's going to be equal to the exponent, and the 10 is the thing that goes inside. So it's 3 equals log base x of 10. Okay? If I look at the next couple, now I want to go the other way. I'm going to start with the logarithmic form, and I want to change it to an exponential function. Again, I'm going to start with the base. So I'm going to start with the base. That's going to be 3. It's going to be raised to the exponent. Well, remember, the logarithm is equal to the exponent, so that's the t. Equals, well, there's only really one thing left. And again, the exponential function is solved for what's inside the logarithm, so that's the 9. Okay? And the advantage to writing it in this form, in this scenario, because we don't know how to plug logarithms into our calculator yet, I can easily see that the t value is 2 in this example. Okay? The next one, again, I start with a base. It's going to be 4. The exponent is 3. It's equal to what's inside the logarithm. That's m. And again, the advantage here is I can easily see what m is now, all right, if I do 4 to the 3rd power. And then the last one, again, the base is the x. The exponent is what this guy is equal to. That's the 2. And then this is solved for what's inside the logarithm, so it equals the 81. Okay? And again, I could kind of see what x equals now based on the exponential form. All right? The other nice thing about this, we can evaluate certain logarithms by converting the logarithm to exponential form and then solving the exponential equation. And we're going to solve it by getting common bases, the one method that we know how to solve these things. All right. So we're going to convert it to exponential form, then we're going to solve the exponential equation. All right. And that'll allow us to evaluate this thing because we don't know how to plug these into the calculator yet. All right. So for example, if I have log base 2 of 16 and I want to know what this equals, right now I don't know what it equals, so I'm going to say it equals x because I have no idea what this thing equals. Now let's rewrite it in exponential form. The base is 2, the exponent is x, it's equal to 16. And you can probably solve this in your head and see that the x value is 4. But let's rewrite it using a common base. This is 2 to the x. 16 is 2 to the 4th. Now I have the same base. I say the exponents are equal, so x equals 4. All right. So essentially what I'm saying is this thing that I didn't know before, which was x, I can now definitively say that this equals a 4. So now I've evaluated the logarithm. Okay. Same thing with the next one. I don't know what this equals, so I'll call it x. If I convert it, that's going to be 3 to the x equals 27. Right away, you can probably tell that the x equals 3, but let's rewrite it with common bases. That's 3 to the x equals 3 to the 3rd. Now I have the same base. I can say the exponents are equal to one another. And so what that's telling me, it's saying when I evaluate this logarithm, I know what it's going to equal. It's going to equal a 3. All right. And again, we'll learn to plug these into the calculators. But unlike the rest of the functions we've dealt with before, logarithms are very different in that instead of starting by plugging values into the calculator to see how these things work, we start with how they work. And now we're going to learn later to plug them into the calculator. And so they're a little bit reversed in that regard because we need to know a little bit about these things before we can learn to plug them into the calculator. Okay, so now we understand a little bit more about exponential functions in terms of the fact that they're the inverse, logarithmic functions in terms of the fact that they're the inverse of exponential functions. We can evaluate some of these, but the big thing is being able to convert back and forth, writing a logarithmic function as an exponential function, writing an exponential function as a logarithmic function.